Good morning, everyone. Today, we will be learning about geospatial technology and its role in land governance. As we move into the first part of our presentation, let's understand what geospatial technology really means. Geospatial technology refers to a wide range of tools and techniques that help us study and manage the Earth's surface and its features. It is not just about making maps. It is about collecting, analyzing, interpreting, visualizing, and distributing information that is tied to specific locations. Some of the most important technologies under this category are GIS, Geographic Information Systems, used for mapping and analyzing data; remote sensing, RS, gathering information about the Earth using satellites and aerial images; GPS or GNSS, systems that provide precise location information; and other modern tools like drones, LiDAR, and geospatial sensors. In short, geospatial technology is about connecting data with geography. It allows us to capture, store, and present spatial information in a way that supports better planning, decision-making, and governance.
Now that we know what geospatial technology is, let's look at its applications. Geospatial technology is not limited to maps. It is a decision-making tool used in many departments and sectors. Some important applications are: urban planning helps design better cities, roads, drainage systems, and housing layouts. For example, city planners use GIS to decide where new schools, hospitals, or roads should be built. Environmental management, used to monitor forests, rivers, wetlands, and pollution levels. This helps in conservation and sustainable use of natural resources. Land and natural resource inventory, very important for departments like revenue, forest, soil, agriculture, and water resources. Geospatial data helps in maintaining land records, mapping soil quality, planning irrigation, and monitoring crop health. Disaster management, used to predict, prepare, and respond to disasters like floods, earthquakes, or cyclones. For example, during the Assam floods, satellite images help identify affected villages quickly. Transportation helps in designing new highways, railway lines, and optimizing traffic systems in cities. And beyond these, there are many more uses. Geospatial technology is now touching almost every sector.
Now we'll move to an important concept: geospatial data. Geospatial data, also called spatial data or geodata, simply means information that is connected to a specific location on Earth. It is usually represented by coordinates like latitude and longitude, which help us pinpoint the exact position of a place. But geospatial data is not just about the location. It also includes the attributes or characteristics of that location. For example, a point on the map may show the location of a school. The attribute data could include the school's name, number of students, and facilities. A land parcel on a cadastral map, the attributes could be the owner's name, plot number, land use type, and area. So in short, geospatial data equals location information plus descriptive details. This combination is what makes geospatial data powerful, because it allows us to analyze not just where things are, but also what they are like.
Let's start with the first data collection component, GNSS, or Global Navigation Satellite Systems. GPS, GLONASS, Galileo, and Beidou provide location information. GPS is a satellite-based navigation system that allows users to determine their precise location and track movements in real time. It is widely used for navigation, mapping, surveying, and other location-based applications.
Let's talk about second and third data collection technologies. Remote sensing. Satellites, aerial photography, and sensors collect data on the environment. RS technologies capture information about the Earth's surface, atmosphere, and oceans, providing valuable data for mapping, monitoring, and analysis. Geospatial sensors, cameras, drone technology, LiDAR, radar, and other sensors collect spatial data.
The fourth data collection technique is Geographic Information Systems, GIS, software that analyzes and visualizes spatial data. GIS is a computer-based system designed to capture, store, manipulate, analyze, manage, and present spatial or geographic data. It enables users to integrate various types of data, such as maps, satellite imagery, and demographic information to make informed decisions.
The next component is data visualization. This is about how we present geospatial data in a way that people can understand and use. There are three main methods: mapping and cartography, creating maps to visually represent data; geospatial visualization, using techniques to show data in both 2D and 3D, like terrain models or city models; and web mapping, online platforms such as Google Maps or Bhu-Darshan that allow users to view and interact with spatial data. In short, data visualization turns raw data into clear, usable maps and models that support better decision-making.
Along with data collection, analysis, and visualization, there are a few other key components of geospatial technology. Geospatial standards. These are formats and protocols that make it possible to share data between different systems. Examples are shapefiles, KML or KMZ files. Standards ensure that data collected by one organization can be used by another. Location-based services, or LBS. These are applications that use location data to provide services such as navigation, tracking, or geotagging. For example, apps like Google Maps or Ola Cabs rely on LBS. Geospatial analytics. This is about applying advanced techniques to analyze spatial data. For example, spatial regression or network analysis to identify patterns and make better decisions. Together, these components make geospatial technology more powerful and useful in real-world applications.
Now let's look at some important portals for geospatial technology. National Geospatial Service Portal. This portal acts as a gateway to different geospatial services and datasets, helping users access maps and spatial information for planning and governance. ISRO Earth Observation Data Hub, Bhu-Nidhi. Managed by ISRO, this portal provides satellite-based Earth observation data and services. It is widely used for research, environmental monitoring, agriculture, and disaster management. These portals are important because they make reliable geospatial data easily available to government departments, researchers, and even the public.
Another important set of portals are Bhuvan and Odisha 4K Geo Services. ISRO's Geo Portal, Bhuvan. This is India's own Geo Portal developed by ISRO. It provides satellite images, maps, and other geospatial services. Bhuvan is often called India's version of Google Earth, but it is more focused on government and development projects such as agriculture, water resources, and disaster management. Odisha 4K Geo Services. This is a state-level portal developed by the government of Odisha. It provides geospatial data for both rural and urban development. It is used for planning infrastructure, monitoring natural resources, and supporting e-governance at the state level. These examples show how both national and state-level portals are making geospatial data more accessible for governance and development.
Now let's look at two more portals that support geospatial technology. Hexagon Geospatial Portal. This is an international platform that offers a wide range of geospatial services and data. It is widely used in industries such as urban planning, utilities, transportation, and natural resource management. India Geospatial Education Portal, that is IGET. This is an educational portal designed to build knowledge. It provides tutorials, training materials, and resources related to geospatial technology.
It is very useful for students, researchers, and professionals who want to learn and update their skills. So while portals like Bhuvan and Bhu-Nidhi focus more on data access, platforms like IGET focus on capacity building and learning.
Next, we come to the Global Navigation Satellite System, or GNSS. GNSS is a collective term used for systems that provide positioning, navigation, and timing services across the globe. It works through multiple satellite constellations orbiting the Earth. These satellites continuously transmit signals, and receivers on the ground, like the GPS in our smartphones or survey instruments, use those signals to calculate precise locations. The key strength of GNSS is that it allows users to determine their position anywhere on Earth at any time with high accuracy. This capability makes GNSS essential not only for daily applications like mobile navigation, but also for surveying, land governance, transportation, disaster management, and scientific research.
Now that we know what GNSS is, let's understand how it works. Satellite constellation. A group of satellites continuously orbit the Earth. Each satellite sends out radio signals that carry two key pieces of information: its exact position and the current time. Signal reception. A GNSS receiver, like the one in a smartphone or survey instrument, picks up these signals. By measuring the time taken for the signal to travel from the satellite to the receiver, the device can calculate its distance from that satellite. Triangulation. Finally, the receiver uses signals from at least 4 satellites. By comparing the distances and positions of these satellites, it calculates its own precise location on Earth. This method is called triangulation. So in simple terms, GNSS works like a space-based ruler using satellite signals and timing to pinpoint exact locations anywhere on Earth.
Now that we know how GNSS works, let's break it down into its 3 main components, also called segments. Space segment: the satellites orbiting the Earth that continuously send signals. Control segment: the ground stations that monitor these satellites and keep their data accurate. User segment: the receivers we use, such as mobile phones, survey instruments, or vehicle trackers. In the next slides, we will go into each of these segments in more detail. Let's begin with the space segment of GNSS. This segment refers to the constellation of satellites orbiting the Earth. These satellites are the backbone of the system because they transmit the navigation signals that receivers use to calculate location, velocity, and time. Some key points about the space segment. There are usually 24 to 32 GPS satellites in operation. Each satellite takes about 12 hours to complete one orbit around the Earth. The satellites are arranged in 6 orbital planes, each tilted at about 55 degrees to the equator, so that they cover the entire globe. From any point on Earth, at least 5 to 8 satellites are visible at a time. These satellites operate at an altitude of about 20,200 kilometers. In short, the space segment ensures that no matter where we are on Earth, we can always access multiple satellite signals for accurate positioning. Let's talk about the control segment of GNSS. The control segment is a network of ground stations and control centers that monitor and manage the satellites in a GNSS system. Its main job is to make sure the signals from satellites are accurate, reliable, and trustworthy. There are 4 main parts of the control segment. The Master Control Station, MCS, which is the central hub that monitors all the satellites and sends commands to keep them in the right orbit. Ground antennas communicate with satellites. They receive data from satellites and send commands back. Monitoring stations track satellites continuously and check their performance. And data processing centers process information from monitoring stations and generate navigation messages for satellites. In short, the control segment is like the ground team of GNSS, ensuring everything in space works correctly so we can get precise positioning and navigation information.
Let's move on to the user segment of GNSS and see what it does. The user segment is basically the equipment and devices used by people, organizations, and industries to receive and use GNSS signals. These signals help in navigation, positioning, and timing. A GNSS receiver performs the following tasks. Selecting one or more satellites. The receiver chooses which satellites to connect with. Acquiring GPS signals. It captures the signals sent by the satellites. Measuring and tracking. The receiver continuously measures the signals and keeps track of the satellite's positions. Recovering navigation data. Finally, it extracts the navigation information to provide accurate position, speed, and time. In short, the user segment is the part we interact directly with, like GPS devices or mobile phones, that turn satellite signals into useful information for us.
Now that we understand the components or segments of GNSS, let's take a look at the different types of GNSS systems. First, talk about Global Navigation Satellite System, GNSS. GPS, Global Positioning System. Developed by the United States, GPS is the most widely used GNSS system in the world. GLONASS, Global Navigation Satellite System. Developed by Russia, GLONASS is another globally used navigation system that provides reliable positioning. Galileo. Developed by the European Union, Galileo is designed to offer high-accuracy positioning and is interoperable with other GNSS systems. Next, let's look at some regional navigation satellite systems, which are designed to provide positioning and timing services over specific areas. Baidu. Developed by China, Baidu provides positioning, navigation, and timing services primarily for the Asia-Pacific region. IRNSS, Indian Regional Navigation Satellite System. Developed by India, IRNSS is a regional GNSS that provides accurate positioning services over the Indian subcontinent. QZZSS, Quasi-Zenith Satellite System. QZZSS is a regional system covering Japan, designed as a 3-satellite constellation that enhances GPS signals and provides regional time transfer services. Now that we understand the components and segments of GNSS, let's take a closer look at how it actually works. The accuracy of GNSS positioning is largely influenced by the geometric arrangement of satellites, which is measured using the dilution of precision or DOP factor. DOP reflects both the number of satellites in view and their relative positions in the sky, indicating the overall strength and reliability of the satellite constellation. Modern GNSS receivers can automatically select satellites that provide the lowest geometric DOP, or GDOP, ensuring the most accurate positioning possible. There are several types of DOP. HDOP, which indicates horizontal accuracy, VDOP for vertical accuracy, PDOP for 3D positional accuracy, TDOP for timing accuracy, and GDOP, which combines PDOP and TDOP to represent the overall geometric precision of the system. Let's move on to a specialized geospatial technique that significantly improves positional accuracy: differential GPS, or DGPS. This system builds upon standard GPS by applying corrections from known reference points, enabling highly precise positioning.
To achieve higher positional accuracy than standard GPS, we use differential GPS, or DGPS. DGPS works by comparing the observed coordinates at a known reference point with the computed coordinates and calculating the differences, known as differential corrections. These corrections are then transmitted to GPS receivers at other locations, allowing them to refine their own positions and significantly reduce errors caused by atmospheric delays, satellite clock inaccuracies, and other factors. As a result, DGPS provides enhanced accuracy for navigation, mapping, and other geospatial applications.
To understand how differential GPS, DGPS, achieves high positional accuracy, it is important to know its key components. DGPS relies on a system of reference and communication that works together to minimize errors in GPS positioning. The main components are reference station or base station, a stationary GPS receiver installed at a precisely known location. It continuously monitors GPS signals and calculates differential corrections based on the differences between the observed and true coordinates. DGPS receiver, or rover, a mobile GPS receiver that receives the corrections from the reference station and applies them to its own position calculations, greatly improving accuracy.
Building on the principles of DGPS, modern geospatial applications often require even higher accuracy in real time, especially over large areas. This is where Network RTK, or NRTK, comes into play, offering centimeter-level precision using a networked approach. NRTK improves upon conventional RTK by using a network of continuously operating reference stations, or cores, rather than relying on a single base station. This network allows the rover to receive real-time corrections via the internet, achieving centimeter-level accuracy approximately 1 to 2 centimeters. NRTK is particularly useful in urban environments, precision agriculture, and large-scale surveying where high accuracy is essential. Common methods and services used in NRTK include VRS, MAC, and FKP, each designed to provide reliable corrections across wide areas efficiently.
Once we have understood NRTK, it becomes important to explore the role of CORES stations. A CORES network consists of multiple reference stations that operate continuously to provide highly accurate positioning information. CORES stations create virtual base stations, allowing rovers to access long-range, high-accuracy network RTK corrections in real time. These corrections are essential for establishing ground control points, or GCPs, conducting precision surveys, and supporting a wide range of geospatial applications where accuracy is critical.
Let us now explore how Network RTK NRTK works and achieves high precision positioning in real time. Network RTK is an advanced GNSS technique that provides centimeter-level positioning accuracy over large areas. The process begins with a CORES network where multiple continuously operating reference stations collect GNSS data in real time. This data is then sent to the Network Control Center at the Survey of India, Dehradun, where it is processed to generate correction models. These corrections are transmitted to users or rovers via mobile internet technologies such as GPRS, 4G, or NTRIP. Once received, the rover applies these corrections to its own GNSS measurements, enabling it to compute highly accurate positions with centimeter-level precision. NRTK is particularly useful in applications like urban surveying, precision agriculture, and large-scale mapping projects.
To understand how NRTK achieves centimeter-level accuracy, we first need to look at its backbone, the reference stations. The CORES network consists of a series of continuously operating reference stations equipped with high-precision GNSS receivers. These stations continuously collect raw satellite data and transmit it to the Network Control Center, NCC. By maintaining stability and long-term accuracy, the core's network ensures reliable positioning. Additionally, the network covers large geographic areas, which helps improve the accuracy of the corrections applied to rovers in the field. The next key component of the NRTK system is the control center, which plays a critical role in ensuring accurate real-time positioning. The control center receives GNSS data from multiple core stations and processes it to compute correction models using techniques such as VRS, FKP, and MAC. These corrections are then distributed in real time to users via NTRIP. Moving forward from GNSS and NRTK, let's explore another powerful geospatial technology, remote sensing, which allows us to gather information about the Earth's surface without being physically present at the site. What is remote sensing? The term remote refers to something that is far away or not in direct physical contact, while sensing means collecting information, data, or inputs, such as temperature, pressure, or an image. Continuing our exploration of modern geospatial technologies, we now turn to drones, a versatile tool that is transforming the way we collect aerial data. What are drones? Drones, also known as unmanned aerial vehicles, or UAVs, are aircraft that can be remotely piloted by a human operator using a transmitter, or fly autonomously using software-controlled flight plans. They are equipped with various sensors and cameras, allowing them to capture high-resolution imagery, monitor land and infrastructure, and support applications such as surveying, agriculture, environmental monitoring, and disaster management. With their ability to access hard-to-reach areas and provide real-time data, drones have become an essential tool in modern geospatial studies.
Now, what is GIS? A Geographic Information System, GIS, is a computer-based tool for mapping and analyzing things that exist and events that happen on Earth. GIS technology integrates common database operations, such as query and statistical analysis, with the unique visualization and geographic analysis benefits offered by maps. These abilities distinguish GIS from other information systems and make it valuable to a wide range of public and private enterprises for explaining events, predicting outcomes, and planning strategies.
Applications in land governance. Now, let us look at the applications of geospatial technology in the field of land governance. Land registration. Geospatial technologies make the process of land registration more efficient. They help in reducing disputes and improving the accuracy of land ownership records. Cadastral mapping. With accurate cadastral mapping, property boundaries and ownership information can be clearly defined. This is essential for effective land administration. Land use planning. Geospatial analysis plays a vital role in land use planning. It supports sustainable development and helps minimize conflicts by providing a scientific basis for decision-making. Dispute resolution. Land disputes are very common, and geospatial technologies provide evidence-based solutions, making dispute resolution more transparent and fair. Finally, geospatial tools help in tracking changes in land use, land cover, and even property values. This supports better monitoring and informed decision-making in land governance.
Geospatial technology brings several benefits to land governance. It improves data accuracy, increases efficiency by saving time and cost, enhances transparency and accountability, and supports better decision-making for sustainable development. Key challenges in geospatial land governance include poor data, limited skills, weak infrastructure, and inadequate policies.
Thank you.